Welcome to the AIDI Operation Tutorial Series video. This series of videos aims to help machine vision engineers learn how to use AIDI for model training, evaluation optimization, and other operations. This video will guide you step by step on how to use the AIDI Detect module. You will learn the detailed steps and usage tips for functions such as importing images, defect labeling, setting training and inference parameters, model evaluation methods, and secondary development integration within this module.
The Detect module is a frequently used main module in the field, which can locate defect areas on images, output defect categories, the area of the bounding rectangle of the defect on the image, as well as the lengths of the short and long sides of the rectangle, making it convenient for users to control the size of detected defects. The Detect module is commonly used for rough localization of targets and outputting category information of the targets, suitable for defect detection with simple shape features, rough localization of defects or products, and detection of the presence or absence of components. Now let's take a look at the AIDI interface and its main functional areas. Switch mode, change between different labeling modes. For example, defect labeling and ignored area labeling. Label tools. Select different tools for image labeling. For example, free mode labeling tool. Project. Switch between projects or manage project settings. Modules. Select algorithm modules to build detection solutions. Image list. View and manage imported images. Image management. Import or export images and manage image data. Labels. Add, modify, or delete label classes and assign tags to images or views. Training and inference area. Set model training and inference parameters. Evaluation area. Evaluate model performance after training. Using AIDI typically involves the following steps. Step 1. Create an AIDI project. Step 2. Load the defect images needed for training. Step 3. Select an appropriate AIDI algorithm module. Step 4. Label the defects in the images. Step 5. Adjust training parameters and conduct training. Step 6. Run inference on your model. Step 7. Evaluate or optimize your model. If the results are unsatisfactory, go back to Step 5. Adjust parameters or add more images to the training set, and retrain. Once the model meets the desired performance, you can export it for integration into the framework. Through API integration, the model can be embedded into the system software, completing the AI deployment process. This section will introduce the requirements of AIDI for image formats and sizes, and demonstrate how to complete the creation of the project and the import of images. After opening the AIDI software, the first to appear is the project management interface. Here we can select the workspace, click Select Folder, and create a new folder on the desktop. Now the local workspace has been established. Subsequent work can be created within this workspace, which is convenient to maintain and manage the projects. Right-click in the workspace and select New Project. You can name the project based on the workstation, and the defect type to be inspected, for instance. The exact naming convention can be in accordance with the project. In this example, I will name the project after the module. If your image is irregular to de-image, select the normal project. If you need to import other formats or types of images, such as mixed images, 3D images or TIFF images, you can select the corresponding project type. You can also view the user documentation in the Help option of the AIDI menu bar, or consult AIDI's technical personnel to understand how to use this type of project. It is recommended to import PNG and BMP images in the normal image project, and JPG images are not recommended to use. AIDI supports the maximum importable image pixel size of 30,000 by 30,000 pixels. If the image exceeds this size, it is recommended to first use other traditional algorithm tools to crop the image to a size within 30,000 by 30,000 pixels. Now we are showing the interface after the AIDI Detect project is established. Click Import Image in the Image Management area. You can choose to import a single image or an entire folder. This time, we choose to import using the single image option. Select an image. Press Ctrl+A to select all images and choose Open. Click Confirm. After the image is imported, click the plus button next to Input, and select the Detect module. This section will introduce the AIDI View function, such as how to mask out interference areas, crop large images into smaller ones, and how to perform normalization operations after importing images of different sizes. Through this function, you can accurately operate images and improve work efficiency. Next, let's see how to operate. Mask out interference areas. If the defects we detect only appear in the upper half of the image and not in the lower half, we can adjust the view by dragging the selection box with the mouse, then click Apply. At this point, you can see that only the upper half of the image is selected in the Detect module. This way, we can shield the interference of the lower half of the image, and only label and train in the selected area. Next, I will show you the function of dividing large images into smaller ones. If you import an AIDI image that is relatively large, such as over 5 million pixels, and the size of the defect to be detected is very small, such as 5 by 5 pixels, and if you use the entire image for model training, you will need to set a very high detection accuracy, which requires very high computing power. The image division function can solve this problem, and we usually divide the image into multiple parts and then train the model. If the minimum size of the defect to be inspected is 5 by 5 pixels, we usually cut the view to a size of about 2000 for model training. Next, I will demonstrate the cutting method. First, select the view we want to cut, then select Divide. The size of this image is 1250 by 3350 pixels and it can be divided into 6 parts. To prevent information loss when the target is divided into 2 parts by the division line, we can create an overlap by setting the horizontal and vertical intervals to negative values. Then click Divide and click Apply. At this point, you can see that the image has been divided into multiple parts. Next, I will show you how to perform view normalization. Generally speaking, it is recommended to import images of a uniform size to complete the model building, such as using images collected by the same camera at the same workstation. This can reduce the difficulty of model training and improve the detection capabilities of the model. However, if it is necessary to use images of different sizes for training, or if multiple cameras and multiple products are to share the same model, we can normalize the images by adjusting the view to the maximum size of the imported images. The image view we are importing is 1250 by 3350 pixels. If the maximum size of the imported images is 3350 by 3350 pixels, we can set the view to this size and then click Apply. After adjusting the view, it can ensure that all images input to the model are of the same size. Images smaller than the view will be surrounded by black padding. In this example project, we perform detection on the entire image, and the imported image size is consistent, so we do not need to modify the view size. Just click Apply. Image labeling is the foundation for ensuring the efficient learning of the model. In this section, I will show you how to use the software label tool to add, delete, and modify labels, and accurately complete defect labeling to avoid mislabeling and missing labeling. You will see how to use default labels and shortcuts to save labeled data to improve labeling efficiency. Firstly, in the label management area, we enter the name of the target to be detected. Press the Enter key to complete the import of the label. Then select the defect labeling tool. The mouse wheel can zoom in and out of the image, and pressing the Alt key allows you to use the left mouse button to drag the image. First, I demonstrate the labeling method in the free mode. Hold down the left mouse button to start labeling. Drag the mouse to draw a rectangular box to select the target. Release the mouse and select the corresponding defect label to complete the annotation. Next, I demonstrate the labeling method in the standard mode. Click the small triangle next to it. Set the fixed width and height of the annotation rectangle box, and refer to the completed annotation data for settings. For example, if a certain labeled rectangle box has a size of 212 by 112 pixels, we can set the size of the standard rectangle box to width 110 and height to 110. This way, if there are multiple defects of the same size in the image, we can quickly label them using the standard mode rectangle box. You can adjust the position, size, and category of the annotation area in edit mode. Click the annotation we want to modify to adjust the size, position, and category, or right-click to delete. In the Detect module, the rectangular boxes should be as close as possible to the edge of the area to be detected. If the annotation area is too large, it may cause overkill cases in the model, because the area to be detected within the box is proportionately smaller than with a tight-fitting annotation box, which may cause the model to also learn the background area as the area to be detected, leading to overkill. If the annotation area is small, the model may treat the unlabeled area as an okay region during learning. When similar areas appear in product images again, there may be a possibility of underkill cases. Therefore, when labeling, it should be as close as possible to the edge of the target area that needs to be detected. After confirming that the labeling is complete, press the S key on the keyboard to save and proceed to the next image.
Selecting an appropriate training set is a key factor in improving the accuracy of the model. This section will guide you how to use automatic or manual methods to select different defect images for training set, thereby laying a good foundation for the training effectiveness of the model. Firstly, let me introduce the application scenarios of the two division methods. The automatic division method is suitable for the first time picking images for training after completing defect labeling, with the software automatically randomly selecting, saving manual selection time. Manual division method is generally used in the model optimization stage. After obtaining the initial version of the model, if certain defect features are missing in the training set, manual selection can be used to manually add representative images to the training set for the model to learn, enhancing the model's learning ability for defect features present in this image, and reducing the model's underkill and overkill cases.
Next, I will demonstrate how to use automatic division. After the labeling is complete, we click the Training and Inference button. Select the training helper, select Split Dataset, and click Split. The division ratio appears with the default ratio of 70%, indicating that 70% of the images will be used as the training set, and 30% as the validation set. You can see that there are 22 images in this model in the lower left corner of the interface. We click the Split button where the training set has 15 images and the validation set has 7 images. The number of the images in training and validation set is automatically divided according to the ratio set just now. Next, I will demonstrate the manual division method for training sets. After the training is complete, if there are overkill or underkill situations in this image, we need to add it to the training set for the model to learn. Improving the model's recognition results for the shape of this area. We can correctly label the defects in this image. Then select this image, right-click the mouse and choose to add it to the training set. Images labeled with the above green triangle symbol represent the ones that belong to the training set, suitable for learning by the model to improve recognition effectiveness. An image in the validation set is represented by a red triangle, suitable for evaluating the model's recognition effectiveness after training. These images will not participate in model training. Additionally, it is important to ensure that the training set contains variations of all defects or targets to be detected. Before model training, setting the correct parameters is crucial. In this section, I will introduce how to set parameters, such as the number of training epochs, batch size and maximum edge length, and demonstrate how to adjust the corresponding parameters for different scenarios to optimize the model's performance. Number of training epochs. One epoch refers to going through all the images in the training set once. Setting training epochs to 400 indicates that the 16 images in the current training set will be learned 400 times. If the defects are more complex and there are more defect shapes, we can appropriately increase the number of training epochs to improve the model's recognition performance. It is recommended to increase by 100 units each time. When deploying with more defect shapes and data volumes, and more complex detection requirements, it is usually set to 1200 epochs. Batch size set to 4, which means that when the model is trained, it will randomly select 4 images from the training set to merge into a data packet and input it to the GPU for training. We can appropriately increase the batch size to improve GPU utilization, shorten the model training time and enhance the model's recognition performance. However, after increasing the batch size, the amount of data input to the GPU will increase, which may lead to insufficient GPU memory. When insufficient GPU memory occurs, the batch size can be appropriately reduced. Max length. By setting the max length parameter of the image size can be scaled. For example, if the view size of this image is 1250 by 3350 pixels, and the maximum edge length is set to 512, it means that the long side of 3350 will be scaled down to 512, and the short side will be scaled proportionally. Reducing the image size can improve the speed of model training. However, when there are some fine defects on the image that the model cannot recognize, such as this black dot, we can appropriately increase the max length parameter to ensure the model's recognition performance. For example, the long side of this area to be detected in the box is 20 and the short side is 15. When the max length is set to 512, the image with a long side of 3350 will be reduced by nearly 6 times, and this area with a long side of 20 will also be reduced by 6 times, which is about 3 pixels. The software can recognize defects as small as 3 by 3 pixels. However, if it is necessary to strictly control risks and meet higher recognition rate requirements, it is recommended to ensure that the minimum defect size is 5 by 5 pixels. Therefore, when detecting small defects, we can appropriately increase the maximum edge length parameter to ensure that the smallest defect to be detected after scaling is 5 by 5 pixels. Model architecture. There are 3 options to choose from: simple, medium, or complex network. Simple network is suitable for simple detection tasks, such as extracting only the approximate ROI in the view. Medium network is suitable for scenarios requiring faster processing speed where detection precision is not extremely high. Complex network is suitable for most scenarios, providing the highest detection metrics, although its efficiency is relatively lower. These parameters of geometric augmentation and image augmentation can be enabled if similar situations appear on the image to increase the diversity of training samples. If such situations do not appear, it is not recommended to enable these parameters. Hover the mouse over the information icon on the right to see the effect of each parameter. Enabling the vertical flipping parameter indicates that the image will be flipped vertically. Horizontal flip indicates that the image is flipped horizontally. Vertical rotation indicates that the image is rotated 90 degrees each time. Center rotation indicates that the image is rotated 180 degrees each time. Slight rotation indicates that the image is rotated clockwise and anti-clockwise each time. Clicking the gear allows us to see the effect after setting the parameters. The angle range of -10 to 10 indicates that the image will rotate within a range of 10 degrees clockwise to 10 degrees anti-clockwise. The rotation interval is 1, indicating that the image will randomly rotate 1 degree within the set range in each training round. For example, in the first training round, the image will be rotated 10 degrees clockwise for model training. And in the second training round, the image will be rotated 8 degrees anti-clockwise for model training. We can adjust the rotation interval to control the rotation effect. Shift. The parameter 0.01 indicates that the image will be translated within a range of 1% of its own size. For example, if the current view size is 1250 by 3350 pixels, after setting the vertical and horizontal movements, this image will be offset by 12 pixels to the left and right and 33 pixels up and down in the next training round. Scale. The parameter indicates that the image will be scaled up or down according to the set proportion range. Image augmentation contains two main parameters. Illumination augmentation enhances the brightness of the image. Contrast augmentation enhances the contrast of the image data. Since similar situations have not appeared in the current training set images, we have chosen not to enable these parameters. After adjusting the training parameters, we click the training button below the image management, or the head icon next to the module name to start model training. The progress bar for training will be displayed in the upper right corner, showing the remaining time, the device ID of the GPU in use, the current iteration round and the actual total number of iterations. If we find during the training process that some training parameters need to be changed, and we want to terminate the training early, we can click the stop button next to the progress bar. However, for the performance of model training, it is generally not recommended to terminate early. After terminating the training, it is suggested to click the training button again to restart the training. After completing the model training, how to view the model effect and optimize it is very important. In this section, I will show you how to check the model's performance, set inference parameters, and evaluate the final detection results of the model based on the information tools in the evaluation interface. The colored area in the image is the inference results of the model. By hovering the mouse over the rectangular box, we can see the inference performance of the model, which will display the detected category, center point coordinates area of the bounding rectangle, and information about the long and short sides. Pressing the space bar can hide the model inference results and only view the original labeling information. Other shortcut keys can be found in the shortcut key information under the Help option in the AIDI menu bar. Next, let's view the inference results of the images in the validation set. In the image list area, select the validation set, and now all the images in the validation set have been filtered out. Pressing the Q key and W key, and quickly switch up and down to view the images in the list, we can see that all these images are correctly recognized. But there is a situation in this image where an area is incorrectly recognized as syringe. Next, I will show you how to adjust the inference parameters to improve the inference results. Inference mode. There are three modes: quick start, fast inference, and high precision. In quick start mode, the model starts up quickly, but the inference speed is relatively slower compared to the other modes. In fast inference mode, the model starts up slowly, but the inference speed is the fastest. In high precision mode, the startup speed is slightly slower. The inference speed is second only to fast inference, but the precision loss in this mode is the least. The high precision mode is commonly used in the project. Let's take a look at the filter parameters. Maximum target count. This allows you to set the maximum number of targets that can be detected in an image. Class overlap rate. This can control the number of overlapping target areas. The lower the value, the less overlap is allowed. In characteristics threshold, you can filter the model's inference results by setting the range of area, short side and long side for each target class. Evaluation center. Here you can see information on recall rate and precision rate. In the confusion matrix below, the horizontal headers represent the inference results, and the vertical headers represent the ground truth. We select the option region level and quality matrix. Click View Details for more information. We can see that 22 pusher areas labeled manually were all recognized as pusher by the model. The manually labeled rubber stopper area was all correctly recognized as rubber stopper by the model. But an overkill situation occurs here. We can click on the number 1 to quickly filter out this image, in which a background region is incorrectly classified by the model as a syringe area. The confusion matrix is an important tool for evaluating the effectiveness of the model in the project, as it can quickly screen out images with overkill or underkill targets. Category Overview. This will display the number of overkill or underkill targets for each target class, as well as precision and recall rates. Model Details. This will show the total time required to train the model and the average or maximum inference time per image. We are currently using the Quick Start mode with an average inference time of 34.39 milliseconds per image. We select the Fast Inference mode, click Inference, and see that the average inference time per image is 24.23 milliseconds. A better GPU speeds up training and cuts down inference time. We can use these times to evaluate the speed of model inference in the project. When estimating the model inference time in the project, it is recommended to add 20% to 30% more time to the average inference time per image, as machines usually run other software which can occupy the computer resources. Next, let me walk you through how to handle this overkill situation. Now that we have labeled the actual target area and added the overkill image to the training set, we can retrain and check the result. As you can see, there are no inspection errors left after the retraining. Next, I will explain the application scenario of the demo project. The demand for this product detection is assembly check. Users need to check if the components such as needles, syringes, rubber stoppers, and pushers are complete. If the components are complete, the product will be normally transferred to the next process step. If not, the product will be deemed NG and disposed of as scrap. Therefore, our solution is to use the Detect module to label and learn the specific areas, identifying all present components within the product. This data is then fed directly into the machine's detection and decision framework, which evaluates assembly completeness. For example, if the current image is missing a needle, the model will only output the syringe, rubber stopper, and pusher. By processing this output, the system can autonomously identify missing needles and classify the product as defective. Attention! The OK or NG indicator in the lower left corner of the Detect module interface does not represent whether this image is a qualified product or a defective product. It only represents whether there are detection results in the image. You can see that the product in this image does not lack any components and is assembled correctly, and the software still displays the NG indicator in the lower left corner, representing that there are detection results in the image. If there are no detection results on the image, the lower left corner will display a green OK indicator, but this does not represent that the product meets quality requirements. After completing the model training, we need to export the model for use. This section will show you how to export the trained model. We click on the Model option in the upper menu bar of the software, select the Export Model button, choose a directory, and export the current model. This is the model file we export for use. In the Model option, you can also export sample code and projects. By clicking on Model and Sample Code Export, you can export the project, set the language, choose a directory, and then click Export. We can see that this is the exported project file, which includes sample code, sample images, and model files. The Detect module can locate and classify defect areas on images, and is suitable for defect detection with simple shape features, rough location of defects and products, and detection of the presence or absence of components in various scenarios. The accuracy of the labels sets the upper limit for the model's performance. So precise labeling can significantly improve the model's results. When labeling, we should try to fit the target contour and avoid over or under labeling. The confusion matrix is a common tool for model evaluation. In the confusion matrix, we can quickly filter out overkill and underkill images, which is convenient for model optimization. If there are underkill cases, you need to label the actual target area normally. Do not label background areas, and then add the image to the training set for retraining. Thank you for watching. For more tips and resources, we invite you to explore the detailed documentation in the software's help menu, or visit the Acros Technology official website.